So in this lesson, we're going to look at convex and concave lenses. By the end of this lesson, you should be able to show what happens to parallel rays when they pass through convex or concave lenses. You should be able to state what the principal focal point and the focal length of a lens means. You should be able to calculate the magnification of the image compared to the object. You should be able to draw ray diagrams to show how you can locate the image of an object in a lens and also be able to work out its magnification. And you should be able to describe the properties of the images produced by both convex and concave lenses. So first of all, we've got these two lenses. We've got a convex lens and we've got a concave lens. What I want to do is to have a think about what would happen to the rays of light passing through. I've drawn the normals, which are right angles to the boundaries, to start you off here. Have a go at just sketching these yourself, pause the video and then work out what's going to happen to the rays. I'll go through it in a minute. So let's see if you were right. First of all, you can see this one will bend towards the normal because the light slows down. When it gets to here, at this boundary here, that's about right angles to this boundary, that's the normal. So it will speed up and bend away from the normal, and so it goes somewhere like that. The central ray, because it goes in at the normal, will carry on straight and not change direction at all, although the light will slow down and then speed up. And with this one here, just like the first one, the light will slow down and bend towards the normal. Drawing a new normal here at right angles to the boundary, light will speed up and bend away from the normal. And actually that will bring light to focus. So what about the concave lens? Well, here light again will bend towards the normal when it slows down. And if we draw the normal at right angles here, it will bend away from the normal and speed up. So it will be diverged. Light in the middle will go in at the normal, so it will carry on straight through without changing direction. And this one on this side will just be the mirror image of the one at the top. So you can see by looking at refraction, we can show through theory that this lens should focus the light and this lens should diverge the light. So if we use a ray box to produce parallel light and we focus it through a convex lens, you can see it focuses to a point. And that's called the principal focus point. And the length between the centre of the lens and where the parallel light comes to focus is called the focal length. So what I want to do now is to look what happens to these incident rays as I move the lens further back. What I've done is that's my object and it's sending off light in all directions. I've just drawn three rays. The ray that goes to the centre and the ray that just goes through at the top and the ray that just goes through at the bottom. So look what happens as I move my object back away from the lens. It might not be that obvious at the minute, but if I circle this, you can see that when the object is quite far away, it produces rays of light which are nearly parallel. Now that's not that far from the lens. So as soon as an object gets a reasonable distance away from the lens, we can assume that it's parallel light coming to the lens, which means the image will be at the focal point. So a great way to measure the focal length of a lens is to just do this. Take yourself a convex lens, take yourself a ruler, set up a little screen, and if I use a distant object like a tree outside the window and I focus the light from the tree, which will be parallel light by the time it comes to the lens, it should produce an image at the focal point, the principal focal point of the lens, because that's where parallel light is produced. Watch this little video and I'll show you what I mean. By bringing the lens closer and focusing on a distant object with parallel rays, you can see that we've now got an image of my garden. Yes, it's upside down. The distance between the lens and the screen is about 10 centimetres, which is the focal length of the lens. So to sum up the first section, have a go at filling in these gaps here. So you should have got the principal focal point is where parallel rays of light are brought to focus. And secondly, the focal length is a distance from the centre of the lens to the principal focal point. So those are the two definitions you need to know. Now what I want to do now is to show you an experiment on what happens when you bring the object closer, because we know that a distant object produces an image at the focal point and it's inverted, upside down and smaller. What happens to the properties of that image as you bring the object closer to the lens? In this short practical, we're going to look at how the properties of the image change as we bring the object closer to the lens, and we're going to use a filament lamp as the object. We're going to start with the object past 2 focal lengths away, and we're going to move it to before 1 focal length from the lens. So measuring just the size of the filament that lights up, that's 1 centimetre or 10 millimeters. So with the object past 2 focal lengths away, we're going to focus the image onto the screen. You may be able to notice that the bulb is upside down and that the size of the image is about 6 millimeters. So using the equation magnification is image height over object height, that gives a magnification of 0.6, so the image is smaller than the object. So the properties of the image are they're real because light comes from the image. Secondly, it's inverted. Lastly, it's diminished, which means it's smaller than the object. Now we're going to move the object close to the lens and put it exactly on 2 focal lengths away to see what the image property has. So you can see the centre of the bulb where the filament is exactly 20 centimetres away, which is 2 focal lengths. And if we now measure the distance from the screen of the focused image to the lens, we can also see it's identical, it's also 20 centimetres. So measuring the size of the image, we find it's 10 millimeters, which is identical to the size of the object. So the magnification is 1. So at a distance of 2 focal lengths away, it produces a real image, which is inverted, is the same distance away as the object, and the magnification is 1. It's the same size. Now we're going to move the object closer between 2 focal lengths and 1 focal length to see what happens to the properties of the image. You'll notice now to focus the image we've had to move the board further back, so the image is produced further away, and if we have a look, it is now magnified with a size of 25 millimeters. You'll also notice that as the image is now larger than the object, you can see that it's clearly upside down. So the magnification now is 2.5, which means the image is real, inverted and magnified. Now we're going to move the object much closer to the focal length, but still not quite as close as the focal length. And you can see the image has magnified hugely and moved further back away from the lens on the other side. So this is like a slide projector or a projector that you use in school. And the magnification of that is huge because the height is 230 centimeters, and you can even see the individual coils of the filament. There's no point trying to focus a real image when the object is before the focal point because it won't do it. What you produce if you've got your object before the focal point is a magnified virtual image. So looking through this magnifying glass with my object, which is my writing, before the focal length, you can see I get a magnified image. So this image is upright because it's the right way round. It's also virtual because light doesn't come from it, and it is magnified. So now we've seen it through experiment, we also need to be able to draw ray diagrams to show what happens to light as it goes through a convex lens and to prove where the image is produced. I want to just go through some of these key terms with you before I show you ray diagrams of how to draw these. The first one is a real image means that light comes from that image. So you saw in that demonstration that light was focused on a screen, and that light was bouncing, reflecting off the screen, and everyone could see that image. But once I had the object before the focal length, I used it as a magnifying glass, and that's then a virtual image because only you can see it, no one else can around you unless they're looking through the lens as well. Upright means it's the same way as the object, like in a magnifying glass. Inverted means it's upside down. Magnified means it's larger, and diminished means it's smaller. So watch this next video, which takes you through how to draw these ray diagrams, and then I need you to practice them yourself. So I'm now going to show you how to draw lens diagrams or ray diagrams in order to show what is happening to the image as you bring the object closer to the lens. You'll notice the diagram for the convex lens is a straight line with the arrows are shown to show it's convex. We're going to start with the first diagram where the object is represented by the red arrow and it is past 2 focal points away from the lens. In order to locate where the image is, we have to draw 2 rays of light from the object, and where they cross will be where the image is. The first ray we can draw is light that comes off parallel to the top of the object, will be focused through the focal point of the lens. So we can draw that and be certain we know where that is. The second ray of light we know what happens to is one that goes through the centre of the lens is not refracted because it goes in and out of the normal. Drawing these two allows us to locate the tip of the arrow for the image because that's where the lines cross. So you can clearly see that the image is inverted and it's smaller than the object. The object was 2 centimeters, our image works out at only 1 centimeter. So the magnification works out at 0.5. So the properties of the image are real, inverted and diminished. You can see on the next diagram, putting the object at exactly 2 focal lengths gives an image which is also at 2 focal lengths. And the image size is 2 centimeters, the same as the object size as we found in our practical. So the image properties are real, inverted and the same size. Going back to the first diagram, this is where the image is smaller than the object, so this is like a camera where you have a large object and a small image. On the film, or in modern cameras of course, the pixel screen. We're now going to move our object between 2 and 1 focal lengths away from the lens. You can see the image has moved even further away from the lens on the other side and is now magnified. So the properties of the image again are real because light comes from the image and it can be focused on a screen. It is inverted, but this time it's magnified. So this is like the projectors we have in our classroom. You've got a small object and a large image which everyone can see because it can be focused onto a screen. So now let's look at how we can draw a ray diagram for when the object is closer than the focal length of the lens. We first of all draw the ray that's parallel to the axis and one that goes through the centre of the lens. You will see that they diverge, so they're never going to meet this side of the lens and produce an image. But if you look back the other way, light travels in a straight line, and so your brain thinks the light has come from the position that I'm showing you now, where we draw dotted lines because those rays do not actually exist. This then produces a virtual image which only you can see if you look through the lens. You'll notice I've used dotted lines to draw the image, and you can see that it's produced on the same size of the lens as the image. It is upright, it is magnified, and it's virtual because you cannot focus it on a screen. So the use of this would be magnifying glass or a microscope, or for reading glasses. So let's draw one final diagram for a convex lens, which is where the object is closer to the focal length of the lens. And you can see that it produces an even larger virtual image.
So just to sum up, if the object is past 2f, 2 focal lengths, we're going to get images which are smaller than the object, so it's a bit like a camera. They'll be real, light will come from them, or light will focus at that point, and they're inverted upside down. Then you get a projector when the object is between 2 focal lengths and the focal length, and as you bring it closer to the lens, the image gets larger and further away. And finally, when the object is for the focal length, the rays of light diverging at this side. So you have to put your eye here, and your brain thinks the light has come from over here, so we produce a virtual image, which is magnified. So that was convex lenses. So what about a concave lens? Well, a concave lens, instead of coming out and curving out, it curves inwards. And you can see that if we put parallel light onto a concave lens, then the rays diverge as though they've come back from the same point here, which is called the principal focus point.
So let's have a look at a concave lens. The concave lens diverges the light, and it diverges it as though it's come from an imaginary focal point on the opposite side, as shown. So looking through the lens at an object far away, that will produce parallel light, so we will produce a virtual image at the focal point of that lens. So now we can look at how we can draw concave diagrams to show the images produced by an object and also its properties. You'll notice that the symbol for a concave lens is a straight line for the centre of the lens, and this time the arrow is the other way to show it's concave rather than convex. We're going to start with the object before the focal length and then move the object further away. So the first location ray we're going to use is one that goes parallel to the principal axis. This will diverge away as though it has come from the focal length of the lens. The second location ray is the same as for a convex lens. The ray that goes through the middle of the lens will carry on straight. You'll notice this again, the rays don't seem to cross, but if you extrapolate back the ray that has diverged as though it's come from the focal length with a virtual imaginary line, you can see that the rays cross. If you look through the lens from the other side, you see a virtual upright image which is diminished, smaller than the object. This is like a spy hole through the door of a hotel, where if you look through you see a virtual upright image which is very much smaller than the object. So just as a final practice, we're going to draw another ray diagram for when the object is slightly further away from the lens. And you can see the virtual upright image is smaller than it was before.
So in summary, the key thing for concave lenses, and students find this one more difficult to draw, is first of all drawing a parallel ray which then diverges as though it's come from the focal point here. Then draw the other ray that goes straight through the normal without being diverted. And then of course you then have to, where these cross here, that will produce your virtual image, which is diminished and smaller than the object. So let's quickly go through the AQA specification for this section so you're really secure on what you need to know. So it says you need to know that a lens forms an image by refracting light, which we've done. In a convex lens, parallel rays of light are brought to focus at the principal focus. The distance from the lens to the principal focus is called the focal length, and ray diagrams are used to show the formation of images by convex and concave lenses. You need to know that the image for a convex lens can be either real or virtual, or the image on a concave lens is always virtual. It says students should be able to construct ray diagrams to illustrate the similarities and differences between convex and concave lenses. So that is just really producing ray diagrams that I've given you. In your exam, they will start to build that ray diagram for you. They won't expect you to do it from scratch, and they will ask you to fill in the rest of the rays to show where the image is produced. Again, it says in the ray diagrams, the convex lens is represented like that, and the concave lens is represented as shown there. And finally, it says you need to be able to use the equation magnification is image height over object height, and that is given to you in your equation sheet at the front. You don't have to learn that equation. So you should now be able to draw what happens to parallel rays going through a convex and concave lens. You should be able to define the principal focal point and the focal length of the lens. You should be able to use the magnification equation to calculate magnification. You should now be quite confident in drawing both convex and concave lenses, and you should be able to describe the properties of the images produced by concave and convex lenses. I'm going to leave you with that slide there, which shows you all the diagrams that I've drawn today.
you now need to go away and practice those yourself, because the more you practice them, the more familiar they'll be when you come to your exam.